In this video, we will study Kirchhoffs' current law, or KCL. KCL states that the amount of current entering a point must be equal to the amount of current leaving that point. And again, it is based on common sense that the amount of current entering must be equal to the amount of current leaving. It is similar again to the situation where we consider current is water, and you can think of the amount of water entering a point must be equal to the amount of water leaving that point. So if we have, for example, I'm just going to draw a partial circuit. If we have this kind of situation, now this point that I have highlighted, this point, we call it a node. And a node is a point where two or more components are connected together. So let's say there is a current that is flowing in this direction. It's I1, current flowing in this direction. And the other branch is I2, I3, and let's say I4 is going downwards. So if these are four different currents, and now I can apply KCL to this node. So we can apply KCL to that node, and at that node, KCL says that the amount of current I entering must be equal to the current that is leaving that node. So entering must be equal to leaving. So it's very simple, just like KVL that we studied before, that the voltage rise is equal to the voltage drop if you move around a loop. In here, KCL is applied to a node, and at that node, the amount of current that is entering must be equal to the amount of current leaving, because current is not being generated at a point, or it is not getting destroyed at a point. So therefore, by the law of conservation of charge, it has to be that the current that is coming to that point must be equal to the amount that is leaving. So if I apply KCL to this circuit, I will say that the current entering in this situation is I1, and the current that is leaving is I2 plus I3 plus I4. All right, so this is the equation that KCL will give me, and then we can use this equation to solve for other variables. Now, an important point here is that the direction of currents is not important. We can assign any directions to the currents, and we don't really need to know the correct direction at the time when we are assigning the currents. So we can choose the current direction freely. But once we choose the directions, we need to stay consistent and use the same directions of the current. And finally, when we calculate the actual value of the current in the branch, if it turns out to be positive, then it means that our original assumption was correct. And if the current turns out to be negative, then it means that the actual current in that branch is actually flowing in the opposite direction of what we originally assumed. In any case, we will find the correct direction of the current, and we will find the voltages in the circuit, so we will be able to solve simple circuits using KCL. Now, let's apply KCL to a simple circuit example. So for that, I will assume this circuit, that we have two resistors connected in parallel. So we have these two resistors that are connected to a current source, and the value of the current source is 2 milliampere. Now here I'm introducing a different source. It is called a constant current source, and it is represented by an arrow inside a circle, and the arrow tells us the direction of the current, and the number next to the source tells us how much is the current. So what it's saying is that the current, let's say I'm calling it I1 over here, that the current that is coming out of the source is 2 milliampere, and the direction is also specified. Now, a constant voltage source, as we have seen in the past, produces a constant voltage. The amount of current drawn from the voltage depends on the circuit. If you put high resistance, large resistance values, then the current will be small. And if you put small resistor values, then the current will be large. So a voltage source produces a constant voltage between its terminals. On the other hand, a constant current source, as the name implies, it will produce a constant amount of current, in this case, that is 2 milliampere. And the voltage that will be produced because of this constant current will be determined by the rest of the circuit. So for instance, if I have large value of resistance, then this source has to maintain 2 milliamperes. So therefore it will produce a large voltage to maintain the 2 milliampere, and vice versa. So that's just a very simple distinction between the two sources. But for now, let's just assume that we have a constant current source which is producing 2 milliampere, and that 2 milliampere will then flow in the rest of the circuit. Now, in this case, our node is, I'm going to apply KCL to this node. All right, so you can see that we have basically 3 different currents involved. Let me give names to the resistors. Let's say this is R2 and this is R3. And I'm going to assume that the current in R2 is flowing downwards and it is equal to I2. And the current in R3 is also flowing downwards and the value is equal to I3. So at the specified node above, we see that there are 3 different currents that are entering and leaving that node. So let's apply KCL to this node. So KCL says that the amount of current entering should be equal to leaving. And we can see that the current that is entering the node is I1. And the currents that are leaving that node are I2 plus I3. Right? So those are our different current values. And we have already specified how much is I1. In this case, we have specified that is 2 milliampere. All right. Now I want to find I2 and I3. But the problem is that I do not know the voltage drop across R2 and R3. If I knew the voltage drop, then it would be very simple. I could have just used Ohm's law. But in this case, we do not know how much voltage the source will produce because it's a constant current source. So we do not know the voltage. But one thing in this circuit we already know is that all 3 components are in parallel. So the voltage produced across R2, if it is equal to V, some voltage, for example, 10 volts or 5 volts, whatever it is, this voltage and the voltage across R3 is going to be the same because they are in parallel. Similarly, the voltage produced at the source terminal will also be V, the same voltage, because all 3 components are in parallel. So when components are in parallel, the voltage across them has to be the same. So this means I can write these 2 currents in terms of voltages and resistors. I1, we already know that that is 2 milliampere. So this is 2 milli. I2, on the other hand, is the voltage across the resistor divided by the resistor value, which is R2. Similarly, the voltage and divided by the resistor value, so R3. Here I can write it this way, that this will be 1 over R2 plus 1 over R3. Let us give some numbers to the 2 resistors. So let's say R2 and R3 are both equal, and they are both equal to 2 kilo ohms. So we will assume that they are both equal to 2 kilo ohms. Now, if that's the case, then my equation will become, this equation will become 2 milliampere is equal to the voltage divided by 1 over 2 kilo plus 1 over 2 kilo. And 1 divided by 1 kilo is 1 milli, so therefore this will be 0.5 milli plus 0.5 milli. And half and half is 1, so I will have 1 milli, and this is equal to 2 milliamperes. Now this can tell me the voltage. The voltage will be 2 divided by 1, which is 2 volts. So if I connect resistors of 2 kilo ohms, then the voltage will be 2 volts. So now we know that the source, the constant current source, will actually produce 2 volts in this case. Now that we know the voltage across the 2 resistors, the voltage across R2 is 2 volts and the voltage across R3 is also 2 volts. And both of these resistors are 2 kilo ohms. So I can easily find I2 and I3 using Ohm's law now. So from Ohm's law, I can say that I2 will be equal to the voltage divided by the resistance, which is 2 volts divided by 2 kilo ohms, which is 1 milliampere. So I2 is 1 milliampere. Similarly, I3 will be 2 volts divided by 2 kilo, and which is also 1 milliampere. So we have now found the values of the currents that will flow in the two resistors. And you can see that 1 milliampere will flow through R2 and 1 milliampere will flow through R3. Now they are equal, but the sum is equal to 2 milliamperes. So you can see that KCL is satisfied. 2 milliamperes enters the node and 2 milliamperes leave the node. So KCL is satisfied. Also, these two currents are equal because I have chosen R2 and R3 to be equal in value. If I had given them some different numbers, then the currents would have been certainly different in the two branches. Now, this is the directions of the current that I would typically use because it makes sense. But I want to make the point that the choice of the current is completely up to us. We can choose any direction of current that we want. So let's solve the same circuit, but this time I'm going to choose different directions of current. And let's see what result can we get using that calculation. So I'm going to draw the circuit again. We have a source, one resistor, and then another resistor. Here we have 2 milliampere constant current source, and I'm going to apply KCL to this node. We know that a current I1, so I'm keeping I1 the same direction, which is 2 milliampere is entering the node. But this time, let me assume, we redraw it. So this was R2 and this was R3. And we said that R2 and R3 are both 2 kilo ohms. So we gave them equal resistances. And now I'm going to choose the current flowing in this direction, let's say. So I2 is entering the node and I3 is also entering the node. So I have chosen opposite direction for I2 and I3. So I just want to make this point that the choice of the current is not critical. You can choose any direction. And once you choose a direction, then you have to stay consistent with that direction. And by consistent, what we mean, it will become obvious very soon. So now let's apply KCL. According to KCL, the amount of current entering should be equal to the amount of current leaving that node. So the current entering, as you can see, is I1 plus I2 plus I3. All three currents are entering the node. And the amount of current leaving, there is no current leaving the node, so therefore the amount of current leaving is 0. So we got an equation which is different than last time, right? You can see our previous equation was slightly different than this one, but that doesn't matter. So now let's continue and find out how much will be I2 and I3 and how much will be the voltage produced by the source. So I already know that I1 is 2 milliampere. So I can say that I2 plus I3 is equal to negative 2 milliampere, right? I can just write it this way. So now I have chosen the current direction to be going upwards. So in a resistor, we know that the current will always flow from a higher voltage to a lower voltage, which means this current direction assumption will mean that the voltage across this resistor will have this polarity, so that the current goes from high voltage to low voltage. Similarly, the voltage over here will also be of this polarity. So this is the voltage V, and V here too. Both of them are in parallel, so therefore the voltage across them is the same. But now the voltage polarity is different than before. But because of our choice of current, this is the polarity we will have to use. So if I have this voltage across R2, then according to Ohm's law, I2 is equal to V divided by R2. plus I3 is equal to V divided by R3, and this is equal to minus 2 milli. Again, we will do the same process. 1 over R2 plus 1 over R3 equals to negative 2 milli. And we have chosen R2 and R3 both to be equal to 2 kilo ohms. So therefore, I have 0.5 milli plus 0.5 milli equals to minus 2 milli, which is 1 milli equal to negative 2 milli. And now the voltage is negative 2 volts. So you see, we got a voltage of negative 2 volts. So what's the voltage is saying that the voltage V is negative 2 volts, mean it is 2 in magnitude, but the polarity is opposite. All right, so the direction is opposite. So in the actual circuit, the plus is actually on top and the minus is on the bottom. So we got a negative voltage. Now with that voltage, we can now apply Ohm's law and find I2 and I3. So I2 must be equal to the voltage drop across the resistor divided by the value of the resistor R2, which is minus 2 divided by 2 kilo, which is minus 1 milliampere. All right. So I2 is negative 1 milliampere and I3 will be the same because they have the same resistor values. So that is also minus 1 milliampere. So we chose directions of current differently. And in the end, we found that the currents are actually negative 1 milliampere. So what it means is that the current I2 is 1 milliampere, but in the downward direction. And the current I3 is also 1 milliampere, but in the downward direction, which is the same result as we got in the first analysis, the first solution of this circuit, where we have chosen that the currents were moving downwards. And both equations, both solutions give us the same result. So this proves that the direction of the current is not important, and you can choose any direction as long as you stay consistent. And by consistent, we meant that the voltage polarity, you have to choose it correctly once you choose the direction of the current. So now let's see a slightly more complicated circuit. And the circuit is as follows. I have a constant voltage source connected to one resistor, then two more resistors. This one is R1, R2, and R3. This is our node where we will apply KCL. The source voltage is 9 volts, which will produce a current I1. And let's assume two more currents. And I'm going to assume that the currents are flowing in the downward direction. So this is I2 and this is I3. So we have three different currents. To explain this circuit, I will use R1 equals to 1 kilo ohms and R2 and R3 both equal to 4 kilo ohms. All right, so let's apply KCL to the node. So again, KCL will tell us that I entering is equal to I leaving. Now the current entering the node is I1, and the currents that are leaving are I2 plus I3. All right. So we have this equation, but in this case, I have used constant voltage source. And so far, we do not know the value of I1. And because of that, we do not know the voltages, and we cannot really simplify it any further. So the first thing I would like to do so that we can apply KCL afterwards is that I want to find how much is the total current produced by the source. To find the total current produced by the source, I will need to calculate the total resistance of the circuit. So this circuit, I see that R2 and R3 are connected in parallel, which means that they will have the same voltage across them. All right. So first of all, I want to find the equivalent resistance of R2 and R3. So my circuit will look like this. I will have the 9 volts and then R1. And this is, let's say, R4, which is the equivalent resistance of the two resistors that are in parallel. And we know that R4 should be equal to R2 times R3 divided by R2 plus R3. You can see this in one of my previous videos, which is the parallel combinations of resistors. So R4 will be equal to R2 and R3 are both 4 kilo ohms. So we have 4 kilo times 4 kilo divided by 4 kilo plus 4 kilo, which is 8 kilo. So that is 16 times 10 to the 6 divided by 8 times 10 to the 3. And therefore R4 is equal to 2 kilo ohms. So therefore R4 is 2 kilo ohms. Now we have previously selected R1 to be 1 kilo. So this is 1 kilo and we have a 9-volt battery. So now our circuit looks like this. We have now two resistors. One is 2 kilo, the other one is 1 kilo. And both of the resistors are now in series, as you can see, because they have the same current flowing through them. So therefore the equivalent resistance of these two is just the sum of the two. So the final circuit is this, that we have 2 plus 1, so we have 3 kilo ohms and 9-volt battery. So now we can apply Ohm's law, and Ohm's law will tell us that the I produced in this circuit will be equal to the voltage, 9 volt, divided by the resistance, total resistance, which is 3 kilo. So that will be 3 milliampere. So we found that how much current the source will produce. The source will produce 3 milliamperes, which is right I1. 3 milliampere will be flowing in at this point, which is the current I1. So this means that my KCL equation over here, I know how much current will be flowing in that branch. Once we know the current I1, now we can easily find the voltage drop across resistor R1, because we know that the current in R1 is 3 milliampere. So I will, just to give me some space here, I will calculate the voltage drop across R1. The voltage drop across R1, I will call it V1. V1 should be equal to I1 times R1, that's Ohm's law, which is 3 milliampere times 1 kilo ohm, and that is equal to 3 volts. So the voltage V1 is 3 volts. This means I have 3 volts drop here. Okay, so now that I have 3 volts drop at this point, from here I can calculate how much voltage will be dropped across the two resistors. We have studied KVL in previous lectures, Kirchhoffs voltage law. And according to Kirchhoffs voltage law, in a closed loop, the voltage rise and the voltage drop are equal. So therefore, if I go around the loop, I would say that the voltage across R2 must be 6 volt, which means the voltage across R3 will also be 6 volt because they are connected in parallel. And now you can see 3 volts plus 6 volt is a total of 9 volts, which is equal to the source voltage of 9 volts. So 9 volts is because of the source is the rise, and 9 volts is the drop because of the two resistors. So now we know the voltage drop across the two resistors R2 and R3. So I can write my equation now that I1 was equal to I2 plus I3. I1 we found to be 3 milliampere. I2 is the voltage drop across that resistor divided by R2, and I3 is the voltage drop divided by R3, which will be again V times 1 over R2 plus 1 over R3, and that will be R2 and R3 are 4 kilo ohms each, so that will be 1 divided by 4 kilo plus 1 divided by 4 kilo, which will be 0.25 plus 0.25, which will be 0.5 milli, and that is equal to 3 milli, which means the voltage V shall be equal to 3 milli divided by 0.5 milli, which is equal to 6 volts. And this is exactly what we calculated using KVL. Right, so KCL gave us the same result as KVL. So we got 6 volts across the two resistors. Now that we know the voltage across the two resistors, now I can calculate I2, will be equal to the voltage across the resistor divided by the resistor value, which is 6 volt, divided by resistor value was 4 kilo. So that is 3 divided by 2 kilo, which is 1.5 milliampere. Similarly, I3 will be the same value because both the resistors are equal. So that will be also 1.5 milliampere. And now you can see that 3 milliamperes enter the node and 3 milliamperes leave the node. And now you have calculated all the currents, all the voltages in the circuit, and it satisfies all the laws, Ohm's law, as well as the KVL and KCL, so everything is satisfied. All right, so that's it for this video, and I will see you next time. Bye for now.